as the intermolecular forces increase, matter is condensed. So the least condensed state of matter is gases, and we do a whole unit on gases. But now, let's talk about the other states of matter. So liquids. Liquids are the most difficult to model, and it's because gases have very weak intermolecular forces and therefore lots of motion, and so that's very easy to visualize, throw things around. It's very nice and easy. Solids have very strong IMFs, very strong intermolecular forces, and next to no motion, so I can just show you like this is a solid. But liquids are kind of between the two because they have strong intermolecular forces, but they still have quite a bit of motion to them. The strong intermolecular forces of a liquid is a network of attractions, and the stronger those intermolecular forces, the larger the network, the stronger three properties of a liquid will be. The first property of a liquid is its surface tension. Surface tension is a resistance to increased surface area. And for liquids, this happens because molecules within the liquid are attracted, or with increasing intermolecular forces, are attracted to the molecules around it. And you need to remember this is three-dimensional space. So this red molecule actually has molecules in front of it, coming out of your computer screen, and behind it, behind your computer screen, all of which are exerting some sort of attraction on it. And the stronger that attraction is, the stronger this liquid will be held together. And the same goes with molecules at the surface. Molecules at the surface are attracted to the molecules around it, and that's going to hold it in a very particular space. Surface tension is what allows water striders, or those bugs you see in the summer, to glide on top of water. They use the surface tension of water, the attraction of the water molecules for the other water molecules below them, to hold it in place, to resist the increasing of the surface area. And the stronger the intermolecular forces, the more it will resist spreading out, because those molecules are more attracted to each other than they are to the sides of their container. If you've ever given blood, you've seen the second property of a liquid, capillary action. Capillary action is the spontaneous rising of a liquid through a narrow tube. The skinnier the tube, the higher it will rise. This is caused by two opposing forces, adhesive forces and cohesive forces. Adhesive forces is when a liquid is attracted to other substances. So it's the reason when you get in water, you become wet, because the water is adhesive, is attracted to you. Cohesive forces are what keep water molecules together, what keep liquids together. So they're the IMFs. When the attraction for the container is greater than the attraction for the other molecules of the same type, the molecules of the liquid, then you have capillary action. The molecules of the liquid are attracted to the walls of the container and will literally climb up it as their attraction for each molecule above the next. It's also the reason we get a meniscus. With water, water has a higher attraction for the glass than it does for other water molecules. So the meniscus is inverted. But mercury has a higher attraction for other mercury molecules, so its meniscus is convex. Viscosity is another property, or is the last property of liquids that we're going to talk about. It is a resistance to flowing, and the best example I can think of this is think of pouring out a glass of water versus pouring out a glass of maple syrup. Maple syrup is extremely viscous. It resists flowing. Viscosity increases with molecular complexity, which is why maple syrup, a very large and complex and cumbersome molecule, is very viscous. But it also increases with intermolecular forces. The stronger something has an attraction for itself, the more viscous it will be. And that pretty much sums up liquids, believe it or not. Most of the time when you see a liquid on the AP exam, you're going to see it as a multiple choice question. Let's move on. Let's talk about some solids. There are only really two types of solids. The first is a crystalline solid. Crystalline solids exhibit a repeating pattern of their structures. So, for example, all of these would be crystalline solids, and we'll talk about each one of these later. Typically, crystalline solids are ionic salts. However, there are some that are network covalent, and we're going to have a whole section on that in a few minutes. And some are molecular bonds that form. So I paused you for a second so I know where we're at. This is a network covalent. See how that these are all covalent bonds. This is all carbon. In fact, this is diamonds. This is an ionic covalent, and when you have an ionic salt that forms a solid, the attraction between the cation and anion is a sign of Coulombic force, which, remember, the strength of that bond is equal to or proportional to the charge of the first times the charge of the second divided by the distance between them. And this over here, this is water when it forms a solid, so this is ice, and this is a molecular solid. Notice that this is the only one where IMFs are actually going to play a role. This is an ionic bond, this is a covalent bond. Here we have an attraction between hydrogen and oxygen. This is a hydrogen bond. So this, in a molecular solid, is when we'll see a lot of IMF conversation. Solids without an orderly structure, without a repeating pattern, a crystalline structure, are called amorphous solids. They have a lot of disorder in their structures. For example, glass. Glass is this picture B here. Glass is made from silicate, silicon dioxide, but it is super heated above its melting point and then rapidly cooled, and it forms a very viscous material called glass. Glass is an amorphous solid. This amorphous structure is the reason why when you break glass, it breaks into a lot of pieces and doesn't just slough apart along certain bonds. When classifying a solid, we look at its lattice. And a lattice is simply a system of designating the center, or what is the center of each substance, or what is the center atom. So at each point on the center, what are we finding? Are we finding molecules, which would be the case over here with ice? Are we finding ions, which would be the case here with sodium chloride? Or are we finding atoms, which would be the case of what we find here with diamonds? If you find ions at each point in the lattice, then you have an ionic salt. Ionic salts are the strongest. They will have the highest melting points because their bonds are among the strongest, because they're a Coulombic force of attraction. The charge of the first times the charge of the second divided by the distance between them. So ionic salts have the highest melting points. They also are extremely hard, meaning they'll leave a mark on something. And while their attractive forces are all Coulombic, they also have some IMFs that occur between them. Because one end is positive, one end is negative, they will have some dipole between them. But their Coulombic force, the ionic bond, is what is really driving it to be an ionic solid, to be a solid. If at each point in the lattice you find a molecule, a whole molecule, so something bound to something else, you have a molecular solid. Molecular solids have low boiling points because they don't have an actual bond between each one of their lattice points. They just have intermolecular forces holding them in place, so they have lower boiling points, or lower melting points, sorry. And in between those two, ionic solids, which are very strong, very high melting points, and molecular solids, which are very low, or relatively low melting points, you have network covalent solids. So where you have a covalent bond, so carbon bound to another carbon, bound to another carbon, bound to another carbon, bound to another carbon. This would be a diamond. Diamonds are just carbons bound to one another in covalent bonds. So atoms are at each lattice point. Their melting points are actually much higher than you would expect for non-metals to be able to form. And typically when you have a network covalent bond, you have one of three players involved: carbon, silicon, or boron. They're the most common. They will form network covalent bonds most often. Carbon, silicon, and boron commonly will form covalent bonds with themselves and form a network covalent solid or an atomic solid. One example of this is diamonds. Another one would be graphite, where you're writing in pencil with is actually the exact same thing. It's carbon bound to another carbon, but rather than line up with this tetrahedral shape, they line up in stacks on top of one another like pancakes. And each mark on your paper is just a stack of pancakes getting laid out. Carbon also can be used to form buckyballs. Buckyballs are 60 carbons held together in a network covalent solid. And actually this is where a lot of research is being put into right now, because these have extraordinarily high melting points, and they actually are excellent conductors of electricity because there's this massive opening between them. If you want a really good read, Google search buckyballs. Not the plaything that people can get for their desk. You're going to need to look for the scientific one, and you can learn about this really interesting openings in nanotechnology through this semi-recent discovery. Now I know you're probably saying, well, those aren't all of the solids in the universe. What about metals? Metals are solids too. And I say, yes, you are right. Metals are solids. So let's talk about metals. Metals are characterized by a very high thermo and electrical conductivity, meaning they can conduct electricity really well. That's why you don't stand outside in a thunderstorm holding a lightning rod. It's also why you don't touch hot metal, because they will conduct that electricity or that heat to you very, very well. They're also malleable, which means you can bend and shape them. They're ductile, meaning they can be rolled into smaller and smaller wires, or they can be pressed into smaller and smaller wirings. And also, most metals, not all, but most metals are shiny. And with the exception of being shiny, malleability, ducticity, I think that's the correct way of saying that, and the ability to conduct energy, all point to the conclusion that the bonds between metals are non-directional, meaning there's not one side where a bond is being attracted to one side or another. And most, in fact, all metals with the exception of mercury are solid, so that means they also must be very strong bonds. So metals are characterized by a non-directional strong bond that can conduct electricity and heat, is ductile and malleable, signs of a metal. The model of a metal is the model you'll be tested on is the electron C model, where metals are cations that rest or reside in a sea of electrons. And if you are to apply, say, an electrical current to them, the way that works is an electron comes in here and bumps into this electron and bumps that electron that bumps this electron that comes out on the other side. Kind of like shooting pool balls across a pool table that has lots and lots of balls spread out across it. Now, metals can be mixed, just like liquids can be mixed, into solutions. And when you make a metal solution, you're actually making what's called an alloy. And there are two types of alloys. You can have a substitution alloy or an interstitial alloy. A substitution alloy is when one element replaces another in the solid. So, for example, brass is a substitution alloy, where 2/3 of the metal of brass is copper and 1/3 is zinc, meaning zinc simply came in and displaced one of the coppers. Another substitution alloy would be sterling silver. Sterling silver is 93% silver and 7% copper. or pewter, which is 85% tin, 7% copper, 6% bismuth, 2% antimony, and so on and so forth. You don't have to memorize those different ones. You just need to know that a substitution alloy is when one element substitutes in for another in an alloy. An interstitial alloy is formed when one element goes into the spaces between the metal, or between the other element, between the host element. Just like interstitial in anatomy means the space between, like interstitial fluid is fluid found between two tissues. Interstitial alloys are atoms that go into the space between the element of that metal. So for example, steel is an interstitial alloy in which iron is heated and activated carbon, so coal is put in it and heated as well, and when it comes out, the iron actually is around the carbon, and that increases its strength. And the different types of steel simply depend upon the percentage of carbon in the iron crystals. So let's go back to the three main types of solids again: network covalent solids, ionic solids, and molecular solids. Network atomic solids, or network covalent solids, are ones in which atoms are found at each of the lattice points. So for example, in diamond, there is a carbon at each point in its lattice. Network atomic solids are strong directional covalent bonds, and they're typically rather brittle. They won't conduct electricity, and most of them are carbon-based. You'll see a couple that are silicone-based, and when you see silicone-based, you're entering the world of geology. So APES people, you're going to be doing a lot with silicone-based network atomic solids. So for example, both diamond and graphite are both network covalent solids, while diamonds have a tetrahedral structure to them. Each of these bonds is at 109.5 degrees. It takes a lot of energy to break one of those covalent bonds, because you can't just break one, you've got to break 1, 2, 3, and there'll be a fourth one up here to get one of those molecules out. Graphite also is a carbon-based network covalent solid, but it layers on top of itself like pancakes, like this. And when you draw a line with your pencil, you're just pretty much peeling off one of these layers. Molecular solids are different than network atomic solids in the fact that there are molecules at each lattice point rather than atoms. So for example, ice or dry ice, which is solid carbon dioxide. And also in this group are things like phosphorus and sulfur allotrophs. An allotrope simply means many forms. So S8 would be a molecular solid because at each point on a lattice structure, when sulfur forms a solid, there's actually sulfur with 8 sulfur atoms at each lattice point. Same with phosphorus. Phosphorus would be P4. So while strong covalent bonds hold the molecule together, the attraction between those molecules, what is making it a solid, liquid, or a gas, is only the intermolecular forces. So while intramolecular forces are holding the bonds, holding the molecule together, the thing making it into a solid would be the intermolecular forces. And remember that those are going to increase with increased number of electrons. So it's a bit of a typo here. It shouldn't say larger molecules. It should say the more electrons something has, the larger its intermolecular forces, the more chance it has of becoming polarized, so its polarizability increases, the less entropy it has, so the more likely it is to be a solid or a liquid rather than being a gas. Ionic solids are extremely stable and have very high melting points because the attraction between the ions at each lattice point is a Coulombic force, which is proportional to the charge of the first times the charge of the second divided by the distance between them squared, or the radius squared. So you really could just say distance. They are extremely, extremely strong. So out of your packet, here's a table that summarizes all of that. The next video will be on vapor pressure and phase change, and we are almost done with this second to last unit.